Well, good morning, good afternoon, or good evening, whenever you're watching this virtual conference. My name is Corey Linden. I'm the Director of Engineering at PSN in Erie, PA. First off, I would just like to thank you so much for your time. I'm an engineer. I know you guys are engineers and scientists and purchasing people and manufacturers, and any more time is really our asset. So thank you for taking your time to come to the conference and to hang out and to watch, this video. I would like to tell you a little bit about PSN and where we came from, but most importantly, my goal at the end of this is to make sure that you see the relevance of who we are and how we could maybe assist you in your project efforts. PSN is an engineering consulting firm that's been around for about 30 years. We started as a very small consulting group, mostly working on legal cases and failure analysis. And in those 30 years, we've grown to a team of 30 people or so, give or take, of scientists, engineers, physicists, chemists, technicians, and more importantly, we've grown in expertise and relevance, and especially in the medical market, we have so much experience that I think is very valuable. We like to talk about what we call the PSN Trifecta, or the triangle, and this is really a combination of our three business units. First one being our processing lab. We essentially have every known polymer conversion type in the world under our roof. The second pillar would be our testing lab. We have an ISO 17025 certified testing lab. And finally, we have an engineering services group, which is our part design, mechanical engineering team. And the benefit of working with us is that all three of those pillars work together. And I think that's where we provide the most value. So now with that background and introduction, what I'd like to do is kind of talk about a typical medical device product lifecycle arc. This is where you guys live. And my goal is, as we talk about this arc that you're probably very used to, you see how we fit into the different phases, and maybe it's a little more relevant so you understand, oh, okay, I see how we could work with PSN or where to engage them in things. I keep holding this ridiculous coffee mug that doesn't even have coffee in it, but I love it because it says, engineer, solving problems you didn't know you had in ways you cannot understand. So if you think about a typical ISO project lifecycle for medical devices, you typically will start with, design input phase. You go to the design output phase, then you do verification, validation, and eventually you're ready to go and you go to manufacturing. We work across all of those phases, and depending on what the need is, we can plug in and be a major driver of that project or just a small team. So we'll start with the design input phase. Typically, this is where your company, they really own that. You guys are very deep in a certain area and you guys are the experts. One of the biggest revelations I had, my first job out of college as a mold designer and hot runner designer, is like, oh my goodness, people spend their entire career working on this one part of a mold, this one product. So when we talk about requirements, you know what you need, you know what your customers need. But we can assist you in the design inputs phase. We can assist with market studies, doing comparative product analysis. We do a lot of work in risk assessment and kind of walking through the risk cycle. At the end of the day, the goal is to understand what the market needs, convert it to market requirements, and then send it downstream. And that downstream in the medical device life cycle is typically called the design outputs phase. And this is where a lot of the heavy lifting starts. In this phase is traditionally, you're doing the work of the engineering. The engineering teams are starting with the technical requirements, and you're going through concepting, through ideation, and then from there you're saying, I have these requirements, we have these concepts, which are the top candidates, let's move forward with these. So there's a very formal process that we can either lead you through or come alongside with you guys to be a part of that. And this is just part of our daily work. One of the big things we like to do in the design inputs phase, or design outputs phase, is once we have a good bucket of concepts to select from, then we really start to vet those. And I think one of the areas we differentiate ourselves is that we don't just vet concepts and ideas based on paper analysis. So we try to force as much work left in the project cycle as possible, and do as much testing at the material level and the component level, so that as you go in the rest of the phases, it's quicker, it's more cost effective, less risky, all of those things. So going back to the PSN triangle, our mechanical engineering team, we work with all major CAD models and CAD software, a lot of FEA work. And with our testing lab, one of the things we like to do in the design outputs phase is, if you're doing a material selection activity, how do you really know how good the data is? Oftentimes in data sheets, it's just based on standard testing, but we have the ability to mold tensile bars or flex bars and do a pretty big suite of tests to really help you understand, okay, we have really vetted this material. For instance, if there's a material that is going to be used for 5 years in the field and it's going to be challenged in a lot of environments, the design engineer needs to know, tell me my data and my property when the material has been aged for 5 years, exposed to all kinds of chemicals or cleaning agents, gone through different temperature cycles, exposed to UV, and is used in a strained situation. So rather than designing with standard test data, we can do all of the testing and put that into our FEA models and get accurate models. Additionally, one big thing, especially in the medical market, is what happens after sterilization. You may do all of this testing but forget sterilization. You could be changing the molecular weight, you could be affecting the molecular bonds of the material, which ultimately will affect your material properties and the way the product performs. Again, looking across the product life cycle, we never want to get to the end where we have to do a failure analysis. So the more understanding we can get up front, the better. Thinking about other portions of the design output phase, it's not just what material do I need, but how do I make a thing with this material? So if I'm using a filled material, what orientation will I get with my glass fiber? How does the gate affect it? What are the differential shrink rates between the material as it goes into the mold? How does that affect my part? How does that affect the tolerances I can get? And all of these things can be figured out in the design phase, so that when you start cutting steel, when you start scaling up to manufacturing, you have a good understanding of tolerances, GD&T, all of those sort of things earlier on. With the design input phase the design output phase, especially in the medical market, and we've been working a lot with customers on this, rather than waiting to the verification and validation stage, when you're doing material testing, especially if things eventually need to be tested for VOCs or extractables and leachables, we have the ability to do that testing at the material level that will help with selecting the material, so that way you don't tool up based on a certain material that's not going to let you pass things downstream. We can test those materials up front with very specific test methods we've developed and help you save a lot of time in the end. Just other things to think about, and this is related to testing, that if I have a seal, what's the compression set going to be over time? How do I best make this manufacturable if I'm going to do a welding process or adhesion or screw systems, or all of these things? We have a lot of experience with part design, and we fit that into the design output phase. So we have our market requirements, we've designed a good component or a good system. Now we're moving down the line in the product development life cycle. We're moving to design verification. This is where we figure out, did we build it right? So we have our artifacts, we have our prints and our CAD and our drawings. We're going to start building tools. We have the ability to make prototype tooling. We have a full machine shop. We work with a lot of mold builders in our direct area, so we can quickly turn around steel tooling, not aluminum tooling, but actual steel tooling in both thermoplastic, thermoset, so that we can create not 3D printed models, but actual molded parts, and do testing at the component level of those parts to understand, does this component meet the test and the requirements that were set out in the earlier phases. But if there is other manufacturing or prototype methods that need to be done, we have the ability to do that too. So we can work with plastics, metals, ceramics, glasses. Essentially, if there is a material that needs to be converted to shape, we have the ability to do that. Moving into design validation, this is where we figure out, did we build the right thing? This goes back to the high level requirements that were set at the customer level. One thing that I didn't mention is some of our people have a lot of experience with systems engineering. So understanding, a V cycle of development, we're very comfortable with that. So when we look at verification, validation, oftentimes in verification, it's standard, ISO testing or ASTM testing that fits very well in our 17025 test lab. When you look at validation, oftentimes this is where you need custom test setups. This is something we can help with also. In our full machine shop, we can turn custom jigs or fixtures or test setup, and this is something we do almost on a weekly basis. And that way at a system level, is my system meeting the customer and marketing requirements that we need to in order to feel safe to go to market. A lot of our customers actually use us as their stage gate, so the data that our testing generates essentially gets put into a report, bolted into your system, especially at the VOC level or the extractables and leachables, and that packet gets handed to the FDA. So we are really generating the data that goes to the FDA for approval of this product to go to market. Okay, so we've started at the beginning, we've got our requirements, we've designed an amazing system, we've verified and validated, and we're ready to go. You've gotten approval. Now we're moving to manufacturing. This is another area where we can set up. A lot of us have come out of the Penn State plastics program, so we're very comfortable and familiar and experts in processing, mold design, mold setup. So we can assist with designing molds, getting molds made, qualifying molds, understanding the best process. And recently we've been getting into a lot of even IQ, OQ, PQ activities where customers are relying on us to do those in-house and sometimes even do small-scale production activities. We've gone through obtaining new machines, we have set up processes, we do full validation on all of the parts that need to be validated, and again, that is a data packet that goes to you guys, and that's part of what gets you approval to go to manufacturing. In an ideal world, engineering is perfect, there's never issues with materials, and you have no failures. However, Murphy always seems to show up when we're dealing with things that are made of molecules. In that case, we also can help with failure analysis. Typically, failures are one of a couple things, especially in medical parts. It's either a function of something happened in the environment, or it was a manufacturing issue, or it's something inherent in the design that is causing these failures, or there's a variation in the material lot, like a contamination or a defect, or the ratio of filler is off. So between our processing lab and our testing lab, we have the ability to take a component or a part and break it down to the parts per million and sometimes billion level to look for contaminants, to look for things that shouldn't be there, to make sure that things that should be there are there, to understand, is there something in the gate location that's causing this? So we have kind of built our company on these failure analysis, and then a lot of the other things have come around it. But we have collectively hundreds of years of failure analysis, both with our customers and also working with our customers and legal teams and litigations across market spaces. So I think one of the benefits of working in lots of markets is that we see things where other companies may not see them, because there may be an innovation or a way to solve a problem in the oil and gas space or in the consumer product space that hasn't necessarily made its way to the medical space. This is especially true in failure analysis and especially relevant. So I'd like to thank you for your time. Again, time is our asset. We appreciate it very much. I hope you're getting a lot of value out of this conference and out of this time. If you have any way that we could engage with you or you have questions, get a hold of us. You're not going to talk to salespeople, you're going to talk to us. So when you call our office and get a hold of us, you'll be working with the engineers and the scientists and the chemists directly. So I hope you have a lovely week, and take care. Thanks.